Well, hello everyone. I hope all is well. Today I'm going to talk about how to remove clicks when you are switching audio. I'm going to explain what happens, the reason that we hear clicks, and I'm going to show you a technique for uh, removing those clicks. So the first thing I want to do is I'm going to create a situation where we will actually hear those clicks. I'm going to use a sawtooth oscillator, and I'm going to put that oscillator into a state variable filter, and I will plug in a number into the cutoff so I can roll off some of the high end. Next, I'll create a gain object down here, and then I'll send that into the Easy DAC. So let's just listen to that oscillator and see what it sounds like. Need to give my cutoff some. So that'll be the sound that I'm going to use to demonstrate that. And next I want to create a selector so I can toggle back and forth and give you an A-B comparison between my original solution to the clicking problem and my improved solution to it. So I'm just going to have 3 messages I'll send to my selector to choose turning it off with a 0, choosing my my initial solution in position 1, and then my improved one in position 2. So the idea here is that I want to create a control signal that I can use to toggle that audio on and off. So I'm going to just use a cycle, and the cycle, as you know, is a sine wave that just goes between 0 and 1. I'm sorry, -1 and 1. So it has a period that it is below 0 and an equal period that is above 0. So I just want to test using greater than tilde 0, and I want to test that signal to see if it is in the on position or the off position. Now if it's on, then I want to gate the signal, or I want to open the gate on the signal rather. Move this over to the gate, and then my gate will go into the selector. So basically these two objects are implementing my switching based on my control signal input. So let's listen to my gated signal, and I'll set the cycle. This is a low frequency oscillator, so I'm going to set it to 2 Hertz, and we'll listen to the output. It might be hard to hear that there are clicks happening until I increase my frequency. So there, hopefully you can hear there are a lot of clicks that are being caused by this gate situation. So let me explain why that is happening. I need to know why before we can have a solution. Okay, so let's look at our input, our audio signal. And this line will be our 0 position, and we can imagine our audio signal coming in as it's a complex waveform. Then we'll show our control signal that we're sending in with our sine wave. So it's going to be doing like this. Now, the idea is that we want the signal to be on when that wave is high, and we want it to be off when the wave is low. And the crucial point here is this right here, where we have that zero crossing of our control signal. So let's zoom into that zero crossing. And let's imagine that this is my audio signal, and this is my control signal. And let's say that, you know, my control signal is coming down and it crosses zero and does like that. So this is the point. This is going to be our on section, right? And then down here is we're going to be off. So we look at this transition point, and if we look at our audio signal at that transition point, we see it is right here. It's very high. This is the cause of the clicking. So if you imagine our signal is playing, or it's either not playing, either one, and when we get to this point, the signal is going to jump from wherever it is right here all the way down to zero immediately. Or the other way, if it were transitioning from negative to positive with the control, then it would be going from zero suddenly up to some value that's high. And that fast change between that amplitude is what's causing the click. So ideally, what we're trying to do is we want to transition where the audio signal crosses zero. So instead of immediately doing it when the control signal goes below zero, we want to wait that amount of time before we make our change. And remembering that this is happening at audio rate, this is a imperceptible amount of time from the human brain. This is just a matter of a few samples between when we know we need to change till when we actually make our change. So let's go back to the patch. So the way we're going to do our patch is we're going to use Gen. And if you have not ever used Gen before, you just put a Gen object in your Max patch, and then if you double click on it, it will come up in the Gen editor. And Gen is a completely different language from Max. There does not have the same objects. It's a very purpose-built tool that operates at the signal rate, at the sample rate. So if I look up here in my audio status, I can see my sampling rate is 48,000. So that means that this patch will be passed every sample in the input 48,000 times per second. So it's a very low level sample by sample processing of audio. Very powerful, but also not nearly as flexible or not nearly as interesting programming as in the Max language. Gen is very low level. I guess I shouldn't say not as interesting. It is interesting, but it's a whole different mindset. Now the thing about Gen to remember, there are a limited number of operators. All numbers are floats, and any audio stream, remember, is just a stream of floating point numbers. So you can program in Gen visually, just like you can in Max, using the objects and connecting them with connectors and routing things around from the input to the output. Ultimately, if you notice down here in the Max editor, there's a little C button that says code, and if we click that, you'll see that Max is showing us a language called GenExpr, GenExpression, which is what is truly being created by this patch. And you can write in GenExpression language directly, or you can use the visual patching environment. Now, you probably would want to use the visual environment for most things. There are a few cases where it would be helpful to drop into writing GenExpression directly. Now, there's no performance difference no matter which way you do it. Max will take this patch, it will create this source code from it, it will compile that down, and it will run it natively very quickly. So there's no real performance difference, or I shouldn't say no real performance difference. There's no performance difference depending on how you do it. The only performance difference might be if you write code that is more or less efficient than doing it visually. It just really kind of depends. So that said, the way that I have solved this problem is I am using a Gen code box, and this is this is the GenExpression language version of it. And there's a reason that I use this. I really in my case, with trying to change the trying to declick, there are a lot of if statements, if else kind of logic, and that's difficult to do in Gen visual programming. It's much easier to do in direct Gen code. So inside my Gen patch, I want to send the same signal input, and my control signal is going to go into the second inlet, and then I'm going to route my output from that into selector 2. So when I click 2, we'll be able to hear it. Now, I have already sat down and written and debugged and tested the code that's going into this code box. So I'm not going to pretend that I'm just making this all up during this video. I'm just going to paste that in there, and then we can go through that code and I can explain how it works. But first, let's just listen to what's happening if I use my Gen patch rather than using my sort of naive attempt at declicking or at switching audio over here. So to refresh our ears, here is the clicky version, and here is my declicked Gen version. I hope you're able to hear the difference and if YouTube is correctly playing that audio. I'm just going to quickly run through this patch and how the code works, and if you're not interested in this, then definitely skip ahead. But it might be interesting just to see how this logic works. So whenever a sample is sent into a Gen patch, the Gen patch has no memory in it, so it doesn't remember what came in the sample prior. There are a few different ways that you can cause it to remember things, and one of them is with the history class. So I have a history object that's called already gated, and I'm going to use that variable just to remember whether or not on the last sample I was gated. Now, in this terminology here, gated means the gate is closed and no audio is getting through. Ungated, 0, means that the audio is allowed to go through. So 1 means gated, no audio. 0 means ungated, and we have audio. So the first thing I do is I create a variable called signal for N1 and control for N2, and that just helps me read the code. It makes it more understandable. I'm going to skip over epsilon for now, and we'll talk about these two other logic variables. Should gate. So remember, if our control signal is below 0, then we want to gate the signal. We want to stop the signal. Otherwise, we want to let it through. So I'm just setting should gate to my control signal being less than or equal to 0. That's the signal coming in on the second inlet. Then I want to test to see if my audio signal coming in is at 0. So I do that by taking the magnitude of the signal. In other words, I strip off the sign. I use the absolute function. So the absolute value of signal, and I want to see if it is 0, but the way I do that is I test it to be less than epsilon. So epsilon is a low value that I'm going to call 0. And the reason you do that is because depending on how the actual sampling is done, you won't have that sample value be exactly 0. It might get very small as it approaches 0, but it might, between two samples, it might skip over 0. So that's why I have this epsilon value, is to say, well, when it gets below that amplitude, then I'm going to consider that 0. So now I've set my two Boolean variables, 0 or 1, on whether or not I should be gating, or also whether or not my signal is at 0. So now I set a variable called will gate, and this means I will be gating the signal at the end of this logic. And I'm going to set it, initialize it to 0, meaning that no, I'm not going to gate, the audio is going to go through. So now I just need to test for the times when I need to shut off that audio. So first I say if I should be gating and I'm already gated, and that's my history object, remember. If I should be gating and I'm already gated, then will gate is 1, meaning I'm going to close the door. Else, if I'm not already gating, so I should be gating, but last sample I was not gated. Now I want to be testing my signal for 0. If I do have a 0 signal, then I'll set will gate to 1. So the else to all this is, in other words, if I should not be gating and the signal should be going through, I don't want to just turn it on. I want to leave it off until I get back to 0 again. So I'm testing here if I'm already gated and I don't have a 0 signal, then I'm going to close the gate. So hopefully that makes sense. Finally, after that if else logic, I set my output. So I set out1, which is this outlet, equal to my signal input times not will gate. So remember, 1 in will gate means it's going to be closed. So if it's closed, then it's going to have a 1 value. So not 1 is 0. So it's going to multiply the signal times 0, which is going to be 0. Otherwise, if will gate is 0, meaning allow it through, then not will gate will be a 1. Input signal times 1 will be whatever the input signal is. So that will go out my outlet. And then I set my history variable already gated to the value that I computed for will gate. So that's the whole thing, and hopefully that wasn't too painful, but that's the logic that I came up with to prevent these clicks. So now that knowing how this works, we'll go back and listen one more time. This is the clicky version and the declicked. If I increase my frequency of my control signal, Hopefully that is understandable. Now, the thing about this control signal is that I can get this control up into audio range. I've intended to have it set down low like this, and you can hear the clicks and then the no clicks. The reason I'm setting it up higher is it just makes it exacerbates the problem and creates those clicks. Once you get up into higher ranges for the control signal, then they become audio rate themselves, and they become like an oscillator. And very different sounds when there's clicks and no clicks at audio rate, because the clicks are adding to the impulse that is being repeated. So with a high frequency like 210, the clicky version and the declicked version quite different. All right, so that's where I'm going to leave it today. Hopefully this was helpful, and maybe you enjoyed. If you're not familiar with Gen, maybe this is a good sort of introduction to at least programming in GenExpr. And I'll go forward and talk about Gen some more at some point. I do want to talk about one other thing that is a very good book about Gen. It's called Generating Sound and Organizing Time, Thinking with Gen. And this is a great book. I have learned a ton from it. It really will open your eyes, especially in my mind, the most valuable thing I got from this was this idea of using signals for timing. If you are used to using a metro and using bangs to sequence your events in Max, this book will open your eyes to the advantages of using a signal for timing and all the things that you can do to manipulate that signal. And that's all happening in Gen. So if you're interested, I'll have a link down in the description to this book. And also I will have the patch that we're looking at right now down in the description, so you can try that out yourself. You can copy and paste that patch, and in Max go to File New From Clipboard, and it will open up this patch, and all this code will be in there, and you can play with it and tweak it and see. Maybe you can apply it to your own uses in Max. So that's it. Thanks for watching, and we'll see you next time.